Greetings. Let's start to take a look at applying integration. Now, integration has got many applications in engineering and science. So let's have a look at how we can apply it. Let's start with something nice and simple. Let's say, for argument's sake, that we've been told that we have a constant acceleration of, let's say, 5 meters per second squared. Okay, from that basic piece of information, can we find an expression for velocity? Well, we know that velocity is equal to the integration of the acceleration against time. So what would we get if we solve that? Very simple. V equals, so we've got A and our variable is t, so we add the variable which is t to the 1, and then we mustn't forget our c for constants. Now, does that look familiar? How about if I turn it round this way? You recognise it? Well, it's, if I was to tell you that this c ended up being the initial velocity of the body of the car, for example, it's doing 10 miles an hour, 10 meters per second, whatever, then you might recognise it as being this formula, which is one of the equations of motion. So far so good. Let's have a look at, let's go a bit further. Let's say we want to find the displacement. Let me just shuffle my board up a little bit. So we want to find our displacement, which is s. So that would involve integrating twice. So starting with our formula for the acceleration, if we integrate again, so we've ended up with this. So let's integrate again. Displacement, which we use the symbol s for, if you remember. So I'm going to use this formula. Okay, that would give me as a solution, so AT, so we've got raise the power by 1, so that makes that 2, and then divide by the power. Covered the methods of integration in the previous video, and if you're not following this, you need to watch one of those videos, or one of the other many videos there is on YouTube on how to do integration. We've got our C, so this now has gained a variable of t. Sorry, I missed out my dt on here. Let me just correct my error. And we have our c of constant as always. Does that formula look familiar? Right, this formula here and this one here happen to be two of the three formulas that are the equations of motion that I'd mentioned in a previous video about applying differentiation. So for example, the more common form of them, let me change the colour of my pen here. Let's go into a blue. So let's just shuffle over the little bit. Okay, so if I say, for example, the first one is this, V equals u plus at, and the second one is s equals a half at plus ut. Okay, you notice that these two formulas here, this one is the same as this and this one is the same as this. Okay, now we've already established that this c is actually u, our initial velocity. What would this c be here? You notice it's not in here, there's no other term. This would be our initial distance that we've travelled. So we are making an assumption, in this formula we're making an assumption that we're starting at one position of 0. But of course we could actually be starting 2 meters away, 3 meters away, 10 meters away. So that's what that c would be. So that's the link there. So you can see that from this basic formula, just shuffle back a bit, of here, we've managed to find them. So here what we've got really is a very simple way in these formulas here. Our very first simple application of integration. So previously on a video I showed you going forwards using differentiation, beginning with this formula here for displacement, differentiate it, I ended up with this, integrate it again, it left us with acceleration. So we can see how they're all tied together. So we can work forwards and we can work backwards. Of course these c's are constants, we don't always know what they are, but in this situation we did know. So there's your first step, first application of integration. So to finish this off, let's do a quick application of it. Let's say that we already know that A is equivalent to 5 meters per second squared. Let's say that V at time 0 is equal to 5 as well, 5 meters per second. And we've got this other term here from our doing our integration. So this doesn't normally appear in the standard layout of the formulas, but in our case we've got this. So there's an initial displacement, and let's say that our initial displacement, so that's at time 0, is equal to 2 meters. Okay, so that's what that there that O stands for. Initial, original is probably a better way of putting it. So now it's an O. Okay, so original condition, 2 meters. Okay, so if we say that let's find V and S when we've got a T equal to let's say 3 and 7. So 3 and 7. Okay, so all we do is we just take these numbers, we put them into our formula. So for example, V is equal to, so initial velocity, that's what this stands for by the way, initial velocity, U, you can use either term, is 5, plus acceleration, which is 5, times the time, which is 3. That's quite simple. It just gives us 20 meters per second. And if we substitute in for 7, we will get, so we've got the same initial, same velocity, acceleration, sorry, times, and this time it's times 7, which gives us 40. Per second. Okay, and if we do the other one for displacement, S equals, so we've got a half times, so we've got again 5 for acceleration, and first one is 3 seconds, so it's 3 squared, plus 5 times 3, and 5 times 3 and plus 2 for our initial displacement, 2 meters, and that gives us, so 24.5. If we do this again with 7 seconds, we get a half. You may need a calculator for this version. Half times 5 for acceleration times 7 squared. Okay, so it's 49 times 5 halved, and then plus 2. That equals I'll just fit this in here so I don't run out of space. Plus 124. .5 meters. Okay, should be a meters in there. Always good not to forget to put your units in. Okay, so that's just a simple application of it. So we did the integration, found the other expressions, put the numbers in, did the number crunching, got the answers. Simple as that. And of course this applies in the real world. Thank you.